Welcome back. This is still Ken, and we're still in our course on mechanics. And we are now on lesson 5 of our course, which is all about applying Newton's laws. In this section, or in this video, we're going to continue with our discussion on Newton's laws, but this time, we're now going to apply your Newton's laws into some everyday situations. Let's say, for example, on pushing a cart or sliding along a hill, and so on and so forth. This will be our goals for this lesson. First, we are going to use Newton's first law for bodies in equilibrium. And next, we are going to use Newton's second law for accelerating bodies. And then lastly, we're going to study the types of friction. We begin with our study on particles in equilibrium. So in this lesson, we'll extend the problem-solving skills we began to develop in lesson 4. If you can still remember, on lesson 4, we ended up with your free body diagrams, but the free body diagrams do not end the story of your Newton's laws. We're still going to extend this one to problems and then use your free body diagrams and then your Newton's laws to solve these problems. We'll start with the equilibrium problem in which a body is at rest or moving with constant velocity. That means here we're going to apply your Newton's first law of motion. Next, we'll study objects that are not in equilibrium and deal with the relationship between forces and motion. This is the section wherein going to apply your Newton's second law, your law of acceleration. And then lastly, we'll analyze the friction force that acts when a body slides over a surface. For this video and the following videos, we're going to study first your motions in equilibrium or in non-equilibrium, your equilibrium and non-equilibrium systems, which do not include yet your frictional forces. And after that, we're going to discuss about your frictional forces. And then finally, we're going to include your friction into our study of the system. So, by the way, what's equilibrium? When we say a body is in equilibrium, it is when your body is at rest or moving with constant velocity in an inertial frame of reference. So your systems or your bodies in equilibrium can be mathematically described by your Newton's first law, that is the sum of all your net external force F is equal to 0. And for your net F to be 0, your Fx, your Fy, and then your Fz components should also be all in 0. That's the only way when your net force is 0. If you have the sum of all your F is equal to 0, by that we mean that your body is in equilibrium. Let's have some problem-solving strategy first before we go on to the problem proper. So the first of the strategy, or the first step in solving your problems involving your Newton's laws, is to draw the free body diagram of your system. For the present, and for the present lesson, we can consider the body as a particle, so you can present it as a large dot. But later on, when we go, for example, to torque, which is still, we are still going to apply your Newton's law there, you cannot anymore consider your system as a particle, but since we are now looking at rigid bodies. But anyways, for this lesson, we can consider the body as a particle, so we represent it as a large dot. The next step or the next strategy is to decompose the forces along the x and y directions. That is, we are going to resolve your forces which are not yet in the x and y, those forces which are projected at some angle, into its x and y components. So we draw a wiggly line through each force vector that has been replaced by its component. When we say again your wiggly line, if say for example here, if this is your force vector, okay, and your force vector is at some angle theta, so we resolve this one into its x components and then your y components. So it has here the x, and then it has here the y component. So we draw here a wiggly line, meaning or to signify that we have already resolved your vector force into its x and y components. That is, we have replaced this vector, force vector, into the its component along the x and y axis. The next step is to write Newton's law equation for your Newton's law equation for the system or for your bodies. So you can also apply this one to your Newton's Newton's first law and then your second law. So it's either we have an equation which has the sum of all your net force is equal to 0, or you can have the sum of all your net force is equal to your mass times acceleration. The next strategy is, if there are two or more bodies, repeat all the above steps for each body. So if you have 3 bodies, each body should have its own free body diagram, and then each body should have its own equations of motion. If the bodies interact with each other, use Newton's third law to relate the forces they exert on each other. Okay. And then lastly, make sure that you have as many independent equations as the number of unknown quantities. Then solve these equations to obtain the target variables. What we mean here is that if you have 3 unknowns in your equation, you should also have 3 equations in order to solve your problem. Okay, so for 4 unknowns, you should have at least 4 equations. 4 or more equations will do to solve the problem. So these are our strategies in solving problems involving your Newton's laws of motion. So let's have here an example. So this is a one-dimensional equilibrium problem. This is tension in a massless rope. So a gymnast with mass 50 kilograms suspends herself from the lower end of a hanging rope of negligible mass. So what you can see on the figure is the situation of the gymnast hanging on the ceiling by a rope. The upper end of the rope is attached to the gymnasium ceiling. What is the gymnast's weight? What force, magnitude, and direction does the rope exert on her? And what is the tension at the top of the rope? Let us just repeat the problem. A gymnast with mass 50 kilograms suspends herself from the lower end of a hanging rope of negligible mass. The upper end of the rope is attached to the gymnasium ceiling. What is the gymnast's weight? What force, magnitude, and direction does the rope exert on her? And then, what is the tension at the top of the rope? Let's solve first your first problem. What is the gymnast's weight? So again, our first strategy is to draw the free body diagram for your system. So for your gymnast, the only forces acting on your system is the weight of the gymnast, which is downward. Again, we're looking here at the gymnast. So the forces acting are the weight, which is downwards. So as you can see here, you have a downwards direction of the weight. And then you have the tension that the rope exerts on the gymnast, okay, which is directed upward. Otherwise, if this force is directed downwards, that means your gymnast is not anymore hanging on the rope. It might be that the gymnast already has fallen to the gymnasium floor. So the tension of the rope that the gymnast exerts, or that the rope exerts on the gymnast, is upward, and then the weight is downwards. So that is the free body diagram for your system. Okay, but we know that your weight is just equal to your mass times your acceleration due to gravity. So your weight is equal to 50 kilograms times 9.80 meters per second squared, and that is equal to 490 newtons. So the weight of the gymnast is equal to 490 newtons. For our next problem, we're asked to find for the force, both the magnitude and direction, that the rope exerts on the gymnast. So going back again to your free body diagram, we have your weight of the gymnast, which is downwards, and then we have the tension that the rope exerts on the gymnast, which is upward. We're asked again of the force, the magnitude and direction that the rope exerts on her. That is, our target variable here is the tension that the rope exerts on the gymnast, which is upward. From the free body diagram, we write your equations of motion. So that is just from the sum of all your F, that is equal to your vector that is upward. So you have tension rope on the gymnast, plus your vector that is downwards. So minus the weight of the gymnast, that is equal to 0. So again, we sum here your F into 0 since your gymnast is stationary, hanging on the rope. Okay, so it has, or your system is in equilibrium. But we have already the weight of the gymnast, and we know that the weight is equal to 490 newtons. And you can actually just solve this one directly from your equation. So from this equation here, so you have PR on G minus weight G, that is equal to 0. So your TR on G is equal to the weight of the gymnast. So your TR on G, that is just equal to 490 newtons. And what you can see here is just from your Newton's law of Newton's third law, your action-reaction pair. Okay. What happens, by the way, if the rope is exerting a greater force than the weight of the gymnast? So if that is the case, if the rope is exerting a larger force than the weight of the gymnast, meaning the gymnast will accelerate upwards. If, on the other hand, the weight is greater than the tension that the rope exerts on the gymnast, you have a greater weight than the tension, then your gymnast will accelerate downwards. So since we're talking here about equilibrium, the tension that the rope exerts on the gymnast and the weight of the gymnast are forces with the same magnitude, but they are in opposite direction. For the last part of the problem, we are asked of the tension at the top of the rope, that is the tension at the ceiling. So we have here the free body diagram again on figure B, that is the free body diagram for the gymnast, and on figure C, we're not talking here about the tension on the rope. So for this case here, our body is the rope, so we are analyzing here the body. So for that, for the rope, we are going to have another free body diagram. So downwards is the tension that the gymnast exerts on the rope, and then upwards, that is the tension that the ceiling exerts on the rope here. So again, downwards, this is the tension that the gymnast exerts on the rope, and then here, upwards, that is the tension that the ceiling exerts on the rope. Here, at the middle, we treat your rope as just a particle. So as you can see here, we did not take into consideration the forces that the rope is exerting towards the other bodies. We're just considering here the forces that is exerted on the rope. But as you can see here, the tension that the rope exerts on the gymnast and in the tension that the girl exerts on the rope are actually just the same forces. And these are action-reaction pairs. Okay? So from that, from our free body diagram for figure C, the equation of motion is you have P, C on R, the tension that the ceiling exerts on the rope, plus the negative of the tension that the gymnast exerts on the rope. That is a negative again because you have here a downwards vector force. And that is again equal to 0 since your system is in equilibrium. But since your tension that the rope exerts on the girl and the tension that the girl or that the gymnast exerts on the rope are action-reaction pairs, it has a value of 490 newtons. So that means your tension that the ceiling exerts on the rope is also equal to 490 newtons. So that's an easy problem to solve. Let's have here another problem. Still, we're talking about equilibrium problems. A traffic light weighing 122 newtons hangs from the cable tied to the other cables fastened to the support as in the figure. So what we have here is a traffic light. It hangs from a cable tied to two other supports. So the upper cables make angles of 37 degrees and 53 degrees with the horizontal. So you have here one cable at 37 degrees projected from the upper horizontal, and then another cable projected at 53 degrees from the horizontal. These upper cables are not as strong as the vertical cable. So your vertical cable that we're talking about is this one here. So we have here three cables supporting your traffic light. So these upper cables are not as strong as the vertical cables and will break if the tension in them exceeds 100 newtons. So we can say that if the tension here is greater than 100 newtons, this will break. Okay, so that will break there. And also the same case for your second cable. If the tension exerted here is greater than 100 newtons, this will also break. Okay, so it's not as strong as your vertical cable. The question here is, does the traffic light remain hanging in this situation, or will one of the cables break? So we are asked here to find the tension in each of the upper cables. And the tension in either your cable 1 or your cable 2 must be less than 100 newtons so that your cables will not break. Otherwise, if one of the cables has a tension that is greater than 100 newtons, one of them will break. So you think one of this cable is going to break or not? And consider again that the weight of the traffic light is 122 newtons. So can the two cables support your 122 newton weight traffic light, or will one of the cables break? So let's see. So again, from our strategy, our first step is to draw the free body diagram for your system. Okay, so always remember that one. Step 1 always is to draw the free body diagram of your system. So let's determine the forces that are present here. Do we have your weight? Of course there is. You have your weight here that is exerted by your traffic light. And then do you have friction? Of course none. Do you have normal force? Of course none. You have tension, of course. We have three cables here. And we have one cable that supports your traffic light at the left. It's labeled as tension 1. And then, or the force is labeled as tension 1. And then we have another cable at the right. So it's labeled, the tension is labeled as tension 2. Okay. So we have three forces acting in your system. Now let's draw the free body diagram, and let's consider this one as your origin. So this is how your free body diagram looks like. We have a weight that is downwards, okay, and we have here your two tensions. And as you can see here, if you're going to draw here some parallel line parallel to the ceiling, this angle here is congruent to this angle here, and this angle here is congruent to this angle here. So this is now your final free body diagram for your system. The next step here is to write your equations of motion for your body. But before actually going into writing our equations of motion for your body, let us first resolve your forces into its x and y components, since we have two forces that are projected at some angles. So we have here your tension 1 of your cable 1 at the left. So again, we draw here a wiggly line, and then we project this one onto the x-axis, and then project it at the y-axis. So we have here your T1x, and then we have here your T1y. The same situation or the same case for your tension 2. We draw here a wiggly line to denote that we are decomposing your force, and project to the x-axis. We have here your T2x. Project along the y-axis. We have here your T2y. Your T1x is just an adjacent side, so we can use here your cosine identity. Your T1y is an opposite side of the triangle, so you can use your sine identity. The same is true for your T2 force. So these are the components of your forces for your T1. We have a negative of T1 cosine 37 degrees, and we have a positive T1 sine 37 degrees for the y component. For your T2, we have a positive T2 cosine 53 degrees and positive T2 sine 53 degrees for the x and y components respectively. And then lastly, for your weight, since it has no x component, it is 0 along the x. And we have negative 122 newtons for its y component, since it is again directed downwards. So we already have our free body diagram, and we also have now decompose your forces into the x and y components. So our next job is to write the equations of motion. From the free body diagram, the equations of motion are: you first write the forces along the x. We label this one as equation 1. We have the sum of all your fx is equal to negative T1 cosine 37 degrees plus T2 cosine 53 degrees, and that is equal to 0. Again, we just have two forces along the x. We have here your T1x, which is a negative force, and then your T2x, a positive force. So again, we have here negative T1 cosine 37 degrees plus T2 cosine 53 degrees, and that sums to 0, since our system is in equilibrium. Next, we write our equation of motion for the y component. So we just have we have three forces here. We have your T1y, and then we also have your T2y, and then here we have your weight downwards. So the sum of all your Fy is equal to T1 sine 37 degrees plus T2 sine 53 degrees plus negative Wt, and that is equal to 0. And we do not have any more other forces. So these are just your forces along the, these are just your summation of all your Fy. Next, we now solve the problem. So our target here is, or our target variables are T1 and T2. And we want to find out if the values are below 100 newtons so that it won't break. So again, we need to solve your T1 and T2 from the previous equations and find if either T1 or T2 has a value of greater than 100 newtons. If that is the case, then that cable will break. So solving equation 1 for T2 in terms of T1, that is, again, we have here your equation 1. We just write this one in terms of T2, or we solve for T2 in terms of T1. That is, rewriting. You have your T2 is equal to T1 cosine 37 degrees divided by cosine 53 degrees. So your T2 is just equal to 1.33 times T1. So this value here is equal to 1.33. But we still cannot solve T1 and T2 here. So we have two equations. which we can use to solve for two unknowns. So as you can see here, for two unknowns, we need two equations to solve the problem. Using this equation here, your T2 is equal to 1.33 T1. We use this value for T2 and substitute this one to your equation 2. If you can remember here, this is your equation 2. You have T1 sine 37 degrees plus T2 sine 53 degrees plus negative 122 newtons. That is equal to 0. So we are going to use this equation here. Your T2 is equal to 1.33 times T1 and substitute this one to this equation here. So all the T2s in this equation will be substituted with this value here. So then we have T1 sine 37 degrees plus, as you can see, 133 T1 sine 53 degrees minus 122 newtons. So we have an equation which contains just T1. So we can already solve this one. In solving using your calculators, we find that T1 is equal to 73.4 newtons. So we have your T1 is equal to 73.4 newtons. So that means your T1 or your cable 1 will not break. Okay. Using this equation above, using again this equation here to solve for T2. So you have your T2 is equal to 1.33 times T1, and we already have found that T1 is equal to 73.4 newtons. So 1.33 times 73.4 newtons, that is equal to 94.7 newtons. So your T2 is 94.7 newtons and will not also break. That's good news. So this time let us have a guided exercise activity. Guided exercises activity for particles in equilibrium. For this, at this instance, I want you to get yourselves some sheet of paper where you can write your answers and try to solve the problem yourself. Okay, you can pause the video. You can pause the video while doing the exercises, and then see or play the video again if you like to get the answers. Okay, so are you ready? Let's start. Get your papers now. So this is an adventurous archaeologist problem. An adventurous archaeologist crosses between two rock cliffs by slowly going hand over hand along a rope stretched between the cliffs. He stops to rest at the middle of the rope. The rope will break if the tension in it exceeds 2.50 times 10 to the 4 newtons. And our hero's mass is 90 kilograms. If the angle theta is 10 degrees, find the tension in the rope. And what is the smallest value the angle theta can have if the rope is not to break? Again, an adventurous archaeologist crosses between two rock cliffs by slowly going hand over hand along a rope stretched between the cliffs. He stops to rest at the middle of the rope. The rope will break if the tension in it exceeds 2.50 times 10 to the 4 newtons, and our hero's mass is 90 kilograms. If the angle theta is 10 degrees, find the tension in the rope, and what is the smallest value the angle theta can have if the rope is not to break? So get your papers now. And so if you have your papers now, your first task again is to draw the free body diagram of the system. Pause the video if you're going to draw your free body diagram yet. Do you have your free body diagram now? So does your free body diagram looks like this? If that is the case, then you got the right answer. So the forces acting here are your weight, of course, by the archaeologists, which is downwards. And then we have here two tensions in the rope. So again, we have here the weight of the archaeologists. And then we have here a tension here. And you also have here a tension here. And take note here that this point here is at the midway between the midway of the rope. Okay, so you can label this one as T1 or T2 or any tension that you like. And this is projected at some angle theta. So just like before, if you draw here parallel lines, this is your theta here, and then we have here your theta, just like in your diagram. And resolve your tensions into the X and Y components. So basically, your free body diagram should look like this. Sorry, your next job is to write the equations of motion. Okay, pause the video to write the equations of motion. Are you done? If you're done, let's write the equations of motion. So we write first your equation along the X, or your force sum along the X. So we have two forces along the X, this one and then this one. So we have T2 cosine theta, a positive, plus a negative T1 cosine theta. Okay, and that is, this is negative T1 cosine theta, and that is equal to 0. Or let me rewrite this one. So you have here a negative T1 cosine theta, and that is equal to 0. Did you get the right answer? Now let's write the equations of motion along the Y. So we have here this force here, and then this one here, and also this one here. So we have two positive tension forces. So you have T1 sine theta plus T2 sine theta, and then plus the negative weight that is equal to 0. Did you get the right answers? Next, your target is to solve the problem. So using these equations here, and taking note that actually your T1 is just equal to T2, and you can just name these two tension forces as T. So we're asked for the tension and then the theta of your system. And please try answering the problem by yourselves. These are the answers. For the tension, you'll get a tension of 2,540 newtons and then a theta of 1.01 degrees. So please try solving the problem yourselves. So that's it for this lesson. On the next video, we're going to apply your Newton's second law for bodies that are accelerating. This is still Ken, and see you on the next video.